the airframe. It's this that gives the aeroplane its shape and its strength. It's made mainly of aluminium, a metal that most of us are more familiar with as the drinks can or as the kitchen foil. And we're going to show you how it's possible to make the metal used to wrap up the turkey strong enough to wrap up an aeroplane. Then we'll be looking at the tyres, and we'll be seeing how the polymers are tailored to give the strength, the bounce, the abrasion resistance required of the various parts of the tyres, not to mention retaining the gas which is inside. And finally, we shall come to the really hot spot in the aeroplane, but still not as hot as the designers would like. And the challenge of the future is that the engines may well have to make use of a class of materials which may surprise you: ceramics. This is an RJ, but like most airframes, it's made largely of aluminium alloy. The cooking foil was pure. It was weak, but it was very formable. This contains about 4 weight% of copper. That's about 18 copper atoms for every 1,000 aluminium. And the strength is achieved not by just having the copper atoms present, but by making certain that in the right places between the aluminium alloys. Now, this bar is the same alloy as the aircraft, but the copper is spread evenly throughout the metal. And if I apply a force, I can bend it, because it's not as strong as if we arrange for the copper atoms to be clustered into groups. This bar is exactly the same composition, but this time no bend, because this piece has been heat treated to cause the copper atoms to cluster together, and it's as strong as a bar of steel. In the first film, we're going to see how British Aerospace accomplished this neat scientific trick.
When flying began, aeroplanes were made of wood, string and canvas, with struts to take the compression loads and wire to take the tensions. As aviation developed and different materials became available, a new approach swept the industry. Aluminium alloys were adopted because of their lightness and their strength. As a result of the new material, a radical new shape was to emerge. The modern airframe is basically made up of 3 simple forms: the round hoops, the stringers running along the length of the fuselage, and the outer sheet covering. They're all fastened together by rivets. Rivet, stringer and sheet are all made of similar aluminium alloys. And as we've already seen, the materials come in 2 distinct conditions. In their soft condition, aluminium alloys are ideal for forming sheets and for producing a rivet that won't shatter when hammered, but they don't possess much strength. In their hardened state, the alloys are strong enough for flight but can't be formed. Some way has to be found to form the rivets and panels while they're soft and ductile, then strengthen them for a lifetime's flying. The answer's the same from the largest sheet to the smallest rivet. It uses a recipe which at first sight seems more like cookery than science. It's only when you understand what's going on at the atomic level that you see why the treatment has to be done this way. What goes on at this scale is the same whether the atoms belong to a single rivet or a large sheet. The trick is to shift the copper atoms in the alloy in relation to the aluminium ones. The panel sheet, as it comes from the manufacturers, has to be heated to a temperature close to melting point. At such a temperature, the copper atoms behave like sugar in a hot cup of tea. Individual grains dissolve and disperse the sugar evenly in solution. Of course, the difference between the aluminium sheet and the cup of tea is that tea is liquid and the alloy is solid. It has to be, or that would be the end of the sheet. Metallurgists call this kind of solution a solid solution. With atoms evenly dispersed, the sheet will be formable. Then the atoms have to be tricked in order to keep them in solid solution while cold. This is done by suddenly quenching them in water. There isn't time to move. As the temperature plunges, the copper atoms are trapped in the positions they held while hot, dissolved and dispersed like the sugar in hot sweet tea. In this state, the material is malleable and ductile and can be made into the desired airframe shape or formed. But not for long. After about 2 hours, the atoms start to change position again. They cluster together in an attempt to come out of solid solution, just as sugar precipitates out of cold sweet tea. When the sheet's already been formed, this process, known as natural aging, is a crucial strengthening mechanism. What must be prevented is for an unformed sheet to harden, and the way to stop that is to pop it in the fridge. At sub-zero temperatures, the movement of the atoms is slowed right down, and the sheets can be stored for over a week. Hardening still begins when the sheet is brought back out to room temperature. Once a component has been formed, the natural aging is encouraged. Critical parts made of certain alloys can have their strength boosted by artificial aging. To achieve this requires heating for a few hours at up to 200 degrees Celsius. Such treatment can hardly be given to the whole aeroplane, so most parts harden by natural aging, as the airframes stand in the factory. The whole process is called precipitation hardening, and its ingenuity lies in thwarting atomic equilibrium. After 5 days, the sheets and rivets will have lost practically all their formability and developed twice the strength.